This is the screencast for section 2.6, example 8. Even more analysis. Woohoo! All right. So this problem is extremely hard to factor the numerator. That is a four-term polynomial. Without grouping, and grouping doesn't work in this case, I don't really know how to factor that except for synthetic division. We're going to use synthetic division in finding our end behaviors, but in the meantime, I know positive 1 is left out of my domain. I need to see if positive 1 also makes the numerator equal to 0 in order to find out if that would be an infinite discontinuity or removable discontinuity. So 1 cubed minus 3 times 1 plus 3 times 1 plus 1. So 1 minus 3 is negative 2, plus 3 is positive 1, plus 1 is 2. So positive 1 does not make the numerator 0 as well, so therefore positive 1 would be an infinite discontinuity as well as a vertical asymptote. I'm going to plug in negative x to see what kind of symmetry this function has. Since I ended up with not completely the opposite or exactly the same thing as I started with before plugging in negative x, that means I have neither odd nor even symmetry. Now I know that the asymptotes are not going to be y equals 0 or y equals a constant because the degree in the numerator is larger than the degree in the denominator. So I'm going to have to take positive 1, my k value of the denominator, and put it in synthetic division to see what the other end behavior asymptote is. So with the synthetic division, I can see that my end behavior asymptote is going to be y equals x squared minus 2x plus 1. That's the other asymptote. I have a vertical asymptote at x equals 1, but my end behavior is going to act like a parabola. I can find my x and y intercepts. In this case, since the numerator is very difficult to factor, I can find my x-intercept by using my calculator. My y-intercept I can find easily by plugging in 0 though. So after plugging in 0 for x, I found that my y-intercept is negative 1. Again, the x-intercept is going to have to wait until I can see my calculator just because factoring that and finding out what makes the numerator 0 would be quite difficult. So now that I have as much information as I possibly can, I am going to sketch a graph, the information I found, to make my sketch more accurate. Now I know the ends of my function are going to behave like a parabola, but I'm not really sure where the vertex of that parabola is yet, or how it's going to curve around the outsides, the end behaviors. So instead of sketching a dashed parabola just yet, I am going to use my calculator to kind of see where that goes. So I'm going to graph f of x, and that gives me a better idea of where my sketch is going to go. I can find my x-intercept. So my x-intercept is negative 0.26 comma 0, and I just realized that my y-intercept is in the wrong place. I had calculated it to be 0, negative 1, but put it down as 0, positive 1. No, things happen. Alright, so putting my y-intercept in the right place. Now I can use my calculator to kind of sketch where the rest of this graph goes. The outsides are going to act like a parabola, so I'm going to make it look like a parabola. But then it is going to approach, it's going to go through the x-intercept, through the y-intercept, and then approach the vertical asymptote down to infinity. The other piece is going to come down from infinity at the vertical asymptote and then go back up, finishing off the parabola I started on the other side. Now I can see that my range is negative infinity to positive infinity. No y values are missing from this graph. There is an extrema. There's a minimum right there, which I probably should have found before I graphed. This minimum is at 2, 3, so I'm going to adjust my graph a little bit, make sure my minimum is exactly at 2, 3, and then come back up to finish that parabolic shape. So I have a local min at 2, 3. Now the graph decreases from negative infinity to the vertical asymptote and then decreases after the vertical asymptote until the x value of that minimum. After the x value of the minimum, though, the graph increases to infinity. The function is unbounded. The range goes all the way up to positive infinity and down to negative infinity. Now, the part of the graph where the y values are greater than 0, so the y values are positive. In other words, the graph is above the x-axis. That occurs for x values from negative infinity up until the x-intercept, which we found at negative 0.26. Then the graph goes below the x-axis, so the y values would be negative from negative 0.26 up until the vertical asymptote. And from the vertical asymptote all the way out to positive infinity, the graph is above the x-axis. So the y values would be positive. There are 4 end behaviors to describe. I'm going to start with the end behaviors that describe the, I'm going to start with the end behaviors that describe the ends of the graph towards the outside. The left end of the graph, x will approach negative infinity and the y values will approach positive infinity. Remember, the ends of this graph are following the shape of a parabola, so both ends of the graph are going to go up to positive infinity. A parabola comes from a quadratic formula, even degree, same end behaviors, both pointing up to positive infinity. The end behaviors surrounding the vertical asymptote, both of those, the limit as x approaches 1 from the left will go down to negative infinity, and the limit as x approaches 1 from the right will go up to positive infinity. The now try problem is number 55. Again, the numerator is hard to factor out, but I know that 1/2 cannot be in the denominator, or cannot be in the domain because it makes the denominator 0. 1/2 will also not make the numerator 0, so 1/2 is an infinite discontinuity as well as a vertical asymptote. I'm going to test the function for symmetry by plugging in negative x. Since I didn't end up with the exact same thing I started with or the exact opposite, neither odd nor symmetry, neither odd nor even symmetry, what is neithered, apply here. Since the numerator is difficult to factor, I'm going to wait to find the x-intercept until I graph on my calculator, but I can find the y-intercept. I can work on my other end behavior asymptote by plugging in the k value 1/2 into the coefficients of the numerator in synthetic division. So the other end behavior asymptote is the parabola y equals x squared minus 3/2 x plus 1/4. I'm going to sketch the information that I've got so far to help make my graph more accurate. Then when I graph with my calculator, I can find the minimum at negative 0.18, 0.92, a local min. I can also find my x-intercept at 1.75, 0. And now I have enough information to accurately graph my sketch in a similar shape to what my calculator is showing. So I can see that my range is negative infinity to infinity. The function is decreasing up until the x value of the minimum, then increasing from the x value of the minimum to the vertical asymptote at 1/2. Then from the vertical asymptote 1/2 all the way out to infinity, again still increasing. The function is unbounded because the range goes all the way down to negative infinity and up to positive infinity. The function is above the x-axis. The y values are positive from negative infinity on the x-axis up until the vertical asymptote. Then between the vertical asymptote and the x-intercept, the graph is below the x-axis, so those y values would be negative. Then after the x-intercept, the graph goes back above the x-axis, all the way out to positive infinity. Now the end behaviors on the left and the right of the function, x will go to negative infinity and x will go to positive infinity. Both y values will reach positive infinity. Again, the end behavior asymptote here is a parabola, which is an even degree polynomial, which has the same end behaviors, and they will both go up to positive infinity. The end behaviors about the vertical asymptote, as x approaches 1/2 from the left, the y values are going to go up to positive infinity, and as the the x value approaches 1/2 from the right, the y values are going to go down to negative infinity.